Earlier we have seen that the fundamental difference between the frequency selective fading and the flat fading is that in flat fading we have a single delay, that is all the echoes they are received at a single delay as if we have only one ellipse, and transmitter and receiver they are the two focal points of the ellipse. Whereas in frequency selective fading, we have multiple delays. That is, the echoes are receiving at the receiver with multiple delays. And then we can say that we have multiple ellipses. And all these delays, tau 2, tau 3, tau 1, they are differentiable and we can resolve them and they are distinguishable. So let us understand this frequency selective fading with this figure. So let's say an impulse is launched at a particular time t, and we will get echoes coming at the receiver at different delays. So for example, this is tau 1. At tau 1, we are receiving an impulse, and in this tau 1, we are also receiving all the n multipaths corresponding to ellipse E1. Then this is tau 2, and in tau 2, we are also receiving all the multipaths corresponding to ellipse 2, and then similarly. And all these echoes which we are receiving at different time delays, we will keep on receiving them unless the echo falls below the receiver sensitivity. That means, let's say this is the receiver sensitivity level, is the minimum sensitivity level, and once the echo fall below the sensitivity of the receiver, we cannot be able to recover or resolve them, and the duration between the first delay and the last delay is what we called as maximum excess delay. Why we call it maximum? Because beyond the first delay we have additional amount of delays. Let's say this is additional amount of delay, this is again additional amount of delay, and these delays they are additional and they are called as excess. Therefore we have the term maximum excess delay, and this same thing will repeat at different time instant. Let's say I have launched an impulse at this time, so I will receive different copies at different delays in. And if we need to represent these echoes, how we can represent is like this is h of t1 comma tau 1, that is impulse received at time t1 with the delay of tau 1, and this can be written as h t1 impulse launched at time t1 received with the propagation delay tau 2. Let's say this is h t2 at time impulse is launched at time t2 received with the propagation delay of tau 1, and similarly. So if we notice that in this and this, they both are receiving at a same delay tau 1, but the impulse is launched at different times t1 and t2. So this is basically the same channel coefficient which is studied at two different times t1 and t2, and this is already studied under flat fading, and everything under flat fading would also apply to this. So let's see, for example, if we have this impulse and we have this impulse, this is a tau 1, this is a tau 1, and they are at time t1 and time t2. Now if this t1, this t2 minus t1 is less than coherence time, then these 2 points will almost be same to each other, as if we can say they both are correlated to each other, and in this case we can write h of t1 comma tau n is approximately equal to h of t2 comma tau n. And similarly is the case for at the second delay. If they both the time is less than time difference, t2 minus t1 means time difference is less than tc, we say they are correlated, otherwise we can say they are different. So with this difference in the t1 and t2 and the relation with the coherence time, we can also state that whether we have a slow fading or we have a fast fading. For example, whether it is fast fluctuations or there is a slow fluctuations. Okay, so these are responses. So what we are receiving when an impulse is launched to the system, these are the responses because an impulse is launched at a particular instant of time. Therefore, we called it as channel impulse response. The response, it is the response of the channel when an impulse is launched at the transmitter. This is the response we have received at the receiver. And there is a certain way of describing this impulse response, and that is power delay profile. We have seen it earlier why it is called power delay profile, because there is a profiling across the delay axis. And in this case, if we need to if we want to describe this channel impulse response, we take power delay profile, that is averaged power at a certain delay. And what we get is that, let's say this is the delay axis tau, we have delay tau 1 and tau 2, and this is the averaged over time. So what we get is this, and what this shows is that this shows what is the power of the signal, what is the power of the signal at a certain delay tau 1, and this shows what is the power of the signal at a certain delay tau 2. And also there is another concept, this RMS delay spread. When an impulse is launched, what we receive is not an impulse anymore. Like we launched an impulse at this time. So what we are receiving is not a single impulse, but we have an impulse that is spread over this delay, over the time. So that is, it is spread over tau 1 and let's say this is tau n. So delay which was earlier 0 in case of flat fading, now it is spread out, that is we called it as delay spread. There is a spread across the delay. And what is the RMS of this delay spread? This what we are interested in. So similarly, if we see that in flat fading, what we have seen that when s tilde t is equal to 1, then s of t is cos 2 pi fct, that is we have a continuous wave transmission. And in case of flat fading, this fc got modified to fc plus minus fd comma n. So as a result, we are receiving a whole bunch of frequencies at the receiver. Thus, instead of fc, what we had in flat fading is we are receiving fc plus fc plus fm and fc minus fm. So even though we have sent a single tone, we get a whole range of frequencies over fc. That is, frequency is getting spread in the flat fading, and we call it as Doppler spread. Whereas in this case, frequency selective fading, the impulse is getting spread over the time domain. That is, we have a spread in the delay axis. So the fundamental difference between the flat fading and the frequency selective fading is that we get responses at different delay compared to only one response at a single delay tau 1 in case of flat fading. And in flat fading also, we have channel impulse response, but it was not spread in time. It was located at a one particular location of time. There we had Doppler spread, but whereas in this frequency selective fading, it is spread over the delay axis.